Hi everyone, I'm Yaoting Huang from the Bioinformatics Lab at National Chengcheng University. Today we're going to uncover the power of a polynomial time approximation scheme, PTAS for short. Think about packing for a weekend trip. You can't bring your entire wardrobe, so you aim for the best possible selection under time and space limits. That's exactly what PTAS does for really tough optimization problems. It finds good enough solutions efficiently, and you can make them arbitrarily close to perfect. Over the next few slides, you'll learn what a PTAS is, why it's so important when exact solutions take forever, and the key design tricks behind these smart algorithms. Ready to see how we turn impossible tasks into practical tools? Let's dive in. Now that we've set the stage, let's introduce the idea of a RI-HON approximation algorithm. We say an algorithm is a RI-HON approximation if its solution cost C always satisfies. C times divide by C is less than or equal to RHON, where C time is the optimal cost. In other words, the algorithm's output is guaranteed to lie within a factor of RHON of the optimum. And here's the key takeaway. For nitrogen monophosphide hard problems, no polynomial time approximation can achieve a ratio of exactly 1, unless P equals nitrogen monophosphide, so every efficient approximation must accept some loss compared to the optimal solution. Building on our discussion of RHON approximation algorithms, we now introduce the idea of an approximation scheme. This is an algorithm that, besides the problem instance, takes a parameter epsilon greater than 0 and guarantees a solution within a factor of 1 plus epsilon of optimal. In other words, if C time is the optimal cost and C is the cost our scheme returns, then .x's C times the psi C is less than or equal to 1 plus epsilon. A handy way to think about this is the Chinese proverb wan the, draw the target first, then shoot the arrow, meaning we choose our desired accuracy up front before running the algorithm. When such a scheme runs in time polynomial in the input size n for every fixed epsilon, we call it a polynomial time approximation scheme, or PTAS. Building on our discussion of approximation schemes, let's dive into polynomial time approximation schemes, or PTAS. These algorithms let us get arbitrarily close to the optimal solution by choosing a small epsilon. But watch out, as epsilon shrinks, the running time can explode. For example, a naive PTAS might run in time on the order of n caret 2/epsilon, which grows exponentially in 1/epsilon. Ideally, we want our algorithms to stay polynomial not only in the input size n, but also in 1/epsilon. One way to achieve that is with a running time like O 1/epsilon squared n cubed, which keeps the dependence on epsilon under control while still scaling smoothly with n. Building on PTAS, we now introduce the fully polynomial time approximation scheme, or FPTAS. This approach delivers a solution within a factor of 1 plus epsilon of the optimum, and, crucially, its running time is polynomial in both the input size n and 1/epsilon. For example, a typical FPTAS runs in O 1/epsilon squared n cubed, making it practical even for tight error bounds. Now, let's turn our attention to the subset sum problem. Here, you're given a set of integers s and a target sum t, and you must decide whether there exists a subset of s whose elements add up exactly to t. For example, take s equals 1, 4, 16, 64, 256, 1040, 1041, 1093, 1284, 1344, with t equals 3754. One valid solution is the subset 1, 16, 64, 256, 1040, 1093, 1284, which indeed sums to 3754. This decision question, does such a subset exist, is at the heart of the subset sum problem. Building on our previous example, let's now formalize the subset sum problem. An instance consists of a set S of positive integers and a target value t. In the decision version, we ask, is there a subset of S whose elements sum exactly to t? In the optimization version, we instead look for a subset whose sum is as large as possible without exceeding t. To solve this, we'll first explore a straightforward brute force approach, then refine it into a fully polynomial time approximation scheme. Next up, we'll dive into that brute force algorithm and analyze how it works. Building on our discussion of the subset sum problem, let's dive into the classic brute force approach to the optimization version. We have a set of values x, 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 and a target t, and our goal is to pick a subset whose sum is as large as possible without exceeding t. The brute force solution is simple in concept. Enumerate every possible subset, compute its sum, and keep track of the best one. The real challenge, of course, lies in how to generate and evaluate all of those combinations efficiently. In the next slide, we'll see how to refine this brute force method into a much more practical algorithm. Building on that brute force idea, let's introduce the merge_list operation. It takes an existing sorted list of partial sums and merges it with the same list shifted by a new value bokkid. Formally, if pi1 is our current list, we compute pi by merging pi1 with pi1 plus xi. For example, start with p1 equals 1, 4, 5, and let xi equals 3. Adding 3 to each element gives the shifted list 4, 7, 8. Merging the original 1, 4, 5 and the shifted 4, 7, 8 in sorted order yields the new list 1, 4, 5, 7, 8. This operation efficiently combines sums that exclude the new element with sums that include it. Building on the merge_list operation, here's how our subset sum routine unfolds. We start with an input set S of size n and a target value t. On line 1, we record n, the number of elements in S, while line 2 initializes p as the singleton list, 0. From line 3 onward, we iterate over each element x in S. At each iteration, we form p by merging the existing sums in p with those same sums each increased by x, then immediately discard any sums exceeding our target t. After processing all n elements, line 6 returns the largest sum in p that doesn't surpass t. It's a brute force procedure, but it guarantees an exact solution by exploring every possible subset sum. Now that we've seen the algorithm in abstract, let's walk through a concrete example with s equals 1, 4, 5 and target t equals 11. First, we form p by starting from the sum 0 and adding the first element, x equals 1. So p equals 0, 1. Awesome it. In general, at each step, we take every sum in p and keep both the original sums and those same sums plus the new element x. Formally, p equals p union p plus x. So for x equals 4, we add 4 to each entry of p and merge the results to build p. Then for x equals 5, we repeat that process to get p. After this final step, we simply check whether our target, t equals 11, appears in p. Now let's see how the algorithm builds up all achievable sums, one element at a time. We still have s equals 1, 4, 5, and our target t equals 11. First, we process the number 1. P equals 0, 1. Bills 1. Next, we bring in the number 4. We take every element of p, add 4 to it, and unite those sums with the original set. P equals 0, 1, union 0, plus 4. 1 plus 4 equals 0, 1, 4, 5. In general, once we've built p, including the next element x gives us p equals p union p plus x. Finally, after processing all k elements, we simply check whether our target t appears in p. If it does, there's a subset summing to t. If not, there isn't one. Building on the previous slide, let's walk through a concrete example with s equals 1, 4, 5 and target t equals 11. First, p starts with 0. And when we process x equals 1, we add 1 to every element of 0, giving p equals 0, 1. EB. Next, to form p, we take everything in p and also add 4 to each element. That's 0, 1, union, 0 plus 4, 1 plus 4, which yields p equals 0, 1, 4, 5. Then for p, we union the previous set with each of its elements plus 5. Starting from 0, 1, 4, 5. Adding 5 gives 5, 6, 9, 10, so 10. P equals 0, 1, 4, 5, 6, 9, 10. Since 11 doesn't appear in P, we can't reach the target exactly. Instead, the algorithm returns the maximum achievable sum at or below T, which in this case is 10. In general, at each step we build P equals P union P plus X dot accumulating all reachable sums as we process each element. Now, after seeing how our sets P through P explode in size, let's consider the naive alternative, listing every achievable subset sum. You'd end up with values like 10, 11, 12, 15, 20, 21, 22, 23, 24, and 29. That certainly captures every possibility, but the list grows exponentially as you add more elements. Clearly, this approach becomes impractical for larger inputs, which highlights the need for smarter, more efficient methods to avoid generating an exponentially long list of candidate sums. So, how can we tackle this problem more cleverly? Building on that insight, we'll relax our goal. Instead of hunting down the exact optimum, we're satisfied with any solution whose sum is within a factor of 1 plus epsilon of the best. Take the list 10, 11, 12, 15, 20, 21, 22, 23, 24, 29. Rather than keeping every precise value, we can safely round down or merge close numbers. For instance, treat 11 as 10 or 24 as 23, and you still maintain a 1 plus epsilon approximation. This simple trick slashes the number of candidates and keeps our list manageably small, dramatically boosting efficiency. Now let's see how this idea turns into a fully polynomial time approximation scheme for subset sum. Our inputs are the set S of n items, the target value t, and an error-bound epsilon. We build a sequence of lists L through L, starting with L equals 0. For each item x, we merge the previous list with a copy shifted by x, so we capture every sum that either includes or excludes x. Then we call the trim routine on L to prune out sums that are too close to one another, keeping the list size under control. After trimming, we drop any sums that exceed t. Once we've processed all n items, we pick the largest remaining sum z and return it. Because each merge, trim, and prune step runs in time polynomial in n and 1/epsilon, the overall procedure is efficient and guarantees a solution within 1 epsilon of the true optimum. Now let's see how we trim a sorted list L by a small factor delta, 0 less than delta less than 1, keeping only entries that add significantly new information. We build a new list L by scanning through L element by element. For each y in L, we ask, is there already a z in L that's close enough within a relative error of delta? Algebraically, that means yz/z is less than or equal to delta, or equivalently z lies between y, 1 plus delta, and y. If so, we drop y because z approximates it well enough. Otherwise, we append y to L. The key takeaway: any value y whose nearest predecessor z differs by at most delta can safely be removed. This pruning keeps the list size small while preserving an approximation within a factor of 1 plus delta. Building on that trimming idea, the trim procedure takes a sorted list L of length m and a tolerance delta, and in just OM time it produces a much smaller list L. We start by initializing LBroom with the very first element y and setting last equals y. Then we scan each subsequent element y. If y exceeds 1 plus delta last, we append y to L and update last to this new value. Otherwise, we simply skip it. By doing this, every original value y ends up lying between its nearest kept element last and 1 plus delta last. Yet we throw away any value that can be represented within a factor of 1 plus delta by its predecessor in L. The result is a neatly trimmed list that still captures the approximate coverage of the original values. Now let's see the trim procedure in action with delta equals 0.1 and our list L of values 10, 11, 12, 15, 20, 21, 22, 23, 24, 29. As we scan from left to right, we compare each new value y to the most recent last we kept. If y lies between last and last times, 1 plus delta, we drop it, letting last stand in its place. Otherwise, we keep y and update last to this new value. Here's how it plays out. 10 is our first value, so we automatically retain it. Last equals 10. 11 falls between 10 and 10 times 1.1, so we discard 11 and keep last equals 10. 12 exceeds 10 times 1.1, so we retain 12. Last equals 12. 15 exceeds 12 times 1.1, so we retain 15. Last equals 15. 20 exceeds 15 times 1.1, so we retain 20. Last equals 20. 21 and 22 both lie below 20 times 1.1, so we remove them and continue with last equals 20. 23 exceeds 20 times 1.1, so we retain 23. Last equals 23. 24 is within 23 and 23 times 1.1, so we discard 24 and keep last equals 23. 29 exceeds 23 times 1.1, so we retain 29. In the end, our trimmed list L is 10, 12, 15, 20, 23, 29. To recap, the two key rules are: remove any y for which last is less than or equal to y is less than or equal to last times, 1 plus delta. Retain y if y greater than last times, 1 plus delta. This simple scan and compare approach keeps the list compact, while guaranteeing every dropped value is approximated within a factor of 1 plus delta by its representative. Building on that concrete example, here's the general trimming routine in a nutshell. We start with a sorted list L equals y and a parameter delta. First, we initialize a new list L by taking y as its first element and setting last equals y. Then we scan through each subsequent y in L. Whenever y exceeds 1 plus delta times last, we append y to L braj and update last equals y. Otherwise, we simply skip y. It's effectively represented by the previous last. Once we've processed all values, we return L. The beauty of this approach is how delta tunes our pruning. A larger delta means only big jumps survive, so L stays tiny, the algorithm zips along, but the approximation is coarser. A smaller delta forces us to keep more tightly spaced values, boosting accuracy at the cost of extra entries and extra work. That's the entire trimming routine. Simple, efficient, and driven by the choice of delta. Now that we've seen the high-level idea of trimming, here's the exact procedure in detail. We start with a sorted list, L of length m, and a parameter delta. First, we note m and initialize a new list L twelve containing just the first element y, setting last equals y. Then, for each subsequent element y in L, we ask, does y exceed 1 plus delta last? If it does, we append y to L and update last equals y. Once all m elements have been scanned, we return L as our trimmed list. On the right, the slide highlights the trade-off governed by delta. A larger delta prunes more aggressively, keeping L small and the algorithm fast, but risking coarser solutions. A smaller delta retains more intermediate values, improving accuracy at the cost of extra work. So the key question becomes, how should we choose delta to balance these opposing goals? Building on our discussion of delta's impact on trimming, let's now turn to how we choose delta in our fully polynomial time approximation scheme. Remember, an FPT-AS guarantees a 1 plus epsilon approximation while running in time polynomial in both 1/epsilon and the input size n, for example, O 1/epsilon squared n cubed. Since delta directly affects both accuracy and running time, it has to be tied to epsilon and n. So here's the natural question. Can we simply set delta equals epsilon and still meet our efficiency and precision goals? Building on our previous discussion, let's now zero in on how to pick delta for our fully polynomial time approximation scheme. Recall that an FPTAS delivers a 1 plus epsilon approximation in time polynomial in both 1/epsilon and the input size n, for example, O 1/epsilon squared n cubed. Since delta directly affects both accuracy and running time, you might wonder, why not simply set delta equals epsilon? That only guarantees the 1 plus epsilon factor in a single iteration, not across the entire algorithm. To preserve our overall approximation bound at every step, we instead choose delta equals epsilon / 2n. Building on our choice of delta equals epsilon / 2n, here's a fully polynomial time approximation scheme for the subset sum problem called approx_subset_sum. Given a set S, a target T, and an error-bound epsilon, the algorithm proceeds as follows. 1. Compute n equals and initialize L equals 0, 2. For each element x in S, form a provisional list by merging L with each of its sums plus x. 3. Apply trim to this merged list using delta equals epsilon / 2n. This critical step prunes near duplicate sums, keeping the list size manageable while preserving our approximation guarantee. 4. Discard any sums in L that exceed the target T5. After processing all n elements, let z be the largest value remaining in L and return z as the approximate solution. By controlling list growth through trimming and removing sums above T, approx_subset_sum runs in time polynomial in n and 1/epsilon, and it guarantees that z is within 1 epsilon of the optimal subset sum. Now, let's see this approximation scheme in action with a concrete example. Imagine we have the list L equals 104, 102, 201, 101, and a target sum T equals 308. We'll set our error tolerance to epsilon equals 0.40, meaning we want to find a candidate z nimes, so that the true optimal sum y nimes never exceeds 1 plus epsilon, z nimes, I, e, y nimes, is less than or equal to 1.4 z nimes. To control how we round and trim values at each step, we define delta equals epsilon divided by twice the number of items. Since there are 4 elements, delta equals 0.40/24 equals 0.05. With epsilon and delta fixed, we're ready to proceed step by step and compute an approximate sum z times that meets our guarantee. With our rounding and trimming parameters in place, let's run the classic approximate subset sum routine on the 4 weights 104, 102, 201, and 101 against the target T equals 308. Start with L equals 0, insert 104, now L equals 0, 104, insert 102. We form 0, 102, 104, 206, sort it, then trim away 104. It's too close to 102, leaving L equals 0, 102, 206. Insert 201. Adding 201 to each element gives 0, 102, 201, 303, 407. After sorting, we discard 206, dominated by 201, and drop 407. It exceeds T, so L equals 0, 102, 201, 303. Finally, add 101. We generate 0, 101, 102, 201, 203, 302, 404. Sorting and trimming yields L equals 0, 101, 201, 302. The largest sum not exceeding t and L is 302, so our algorithm outputs 302 as the approximate solution. Continuing from our previous slide, we now process the input list L equals 104, 102, 201, 101 by building partial Tash sum lists, L through L. At each step, we merge in the next element, then prune any sums that are dominated or exceed the target. 1. L starts as 0. 2. Add 104 right-pointing arrow 0, 104. No pruning needed, so L equals 0, 104. 3. Merge in 102 right-pointing arrow 0, 102, 104, 206. Drop 104 because it's dominated by 102, giving L equals 0, 102, 206. 4. Incorporate 201 right-pointing arrow 0, 102, 201, 206, 303, 407. Prune 206, dominated by 201, and discard 407. It exceeds the target, so L equals 0, 102, 201, 303, 5. Finally, merge in 101 right-pointing arrow 0, 101, 102, 201, 203, 302, 303, 404. Remove dominated sums 102 and 203 and any above the target, leaving L equals 0, 101, 201, 302. The largest sum not exceeding our threshold is 302, so the algorithm returns 302 as the approximate solution. Now let's walk through the algorithm steps. On our example, input L equals less than 104, 102, 201, 101 greater than. We start with L equals less than 0, greater than. On 101, 1. At L, we insert 104, giving us less than 0. 101, 4 greater than. At L, we insert 102, which replaces the old 104 and yields less than 0. 102, 206 greater than. The deleted 104 is represented by the new 102. Moving to L, we insert 201, replace 206 with 201, and drop 407 since it exceeds our cutoff, ending up with less than 0, 102, 201, 303, greater than June. Finally, at L, we arrive at less than 0, 101, 201, 302 greater than, and the algorithm returns 302 as its answer. Now that we've arrived at our approximate solution z times equals 302, let's see how it measures up against the true optimum. The actual optimal value, y times, is 307. That's 104 plus 102 plus 101. Forming the ratio y times z times gives 307 300-seconds, which sits comfortably within our guaranteed bound of 1 plus epsilon equals 1.4. Even better, the relative error, y times minus z times slash z time, is only about 0.02, or 2%, well below our epsilon of 0.40. In other words, not only do we satisfy the theoretical 40% bound, but in practice our approximation is much tighter. After confirming that our relative error remains comfortably below epsilon, let's now prove that aprox underscore subset underscore sum is a fully polynomial time approximation scheme for the subset sum problem. We'll split the argument into two parts. First, we show that the algorithm's running time grows only polynomially in both the input size n and the inverse error bound 1/epsilon. Then, we establish the approximation guarantee by proving that the solution value y times, produced by the algorithm, satisfies y times z times is less than or equal to 1 plus epsilon, where z times denotes the true optimum sum. Building on our proof that aprox underscore subset underscore sum is a fully polynomial time approximation scheme, let's walk through its pseudocode step by step. First, we let n be the number of input items and initialize L to the list 0. Then, for each item X in S, we form L by merging the previous list L with a copy of itself shifted by X. Immediately after merging, we apply a trim operation to bound the list's growth, eliminating any sums that lie within a factor of epsilon, 2n, of one another, and we discard any sums that exceed the target t. Once all n items have been processed, the algorithm returns the largest sum z remaining in the final list. Thanks to the trim step, the list never explodes in size, so the overall running time is governed entirely by the polynomially bounded length of these intermediate lists. Now that we've laid out the approx_subset_su algorithm, let's walk through a concrete example showing how our list L evolves over 4 rounds as we insert new values and prune outliers. We start at L with just the single element 0, Helum. In L, we insert 104, giving us 0, 104. Moving on to L, we add 102 and its shifted sum 206, yielding 0, 102, 104, 206. After trimming, we drop 104, effectively representing it by its predecessor 102, and shrink the list to 0, 102, 206. At L, we introduce 201, 303, and 407. Because 206 is too close to 201, we replace it with 201, and since 407 exceeds our target t, we discard it. This leaves 0, 102, 201, 303. Finally, in L, we insert 101, 302, and 404. A last round of trimming maps each pruned value to its nearest survivor, resulting in 0, 101, 201, 302. The algorithm then returns z equals 302 as its final answer. Throughout this process, we rely on knowing the maximum target t and the fixed interval between consecutive list entries, both direct consequences of our epsilon-based trimming strategy. Building on our step-by-step example, this slide shows how trimming keeps each list logarithmically small. We enforce that after trimming, every successive pair of values z and z in list LE satisfies z greater than 1 plus epsilon slash 2n. Because of this fixed multiplicative gap, each LE can only contain the starting value 0, possibly the value 1, and at most log_1 plus epsilon slash 2nt. Additional entries up to our known maximum t. In practical terms, whenever a new candidate y arrives, we remove any existing z in the range. y/1 plus epsilon slash 2n is less than or equal to z is less than or equal to y, keeping z only if y/z greater than 1 plus epsilon slash 2n. As a result, Li grows exactly like a geometric sequence: 0, 1, 1 plus epsilon slash 2n, 1 plus epsilon slash 2n squared, up to t, so its length is bounded by that logarithm. This compact list size is the key to our algorithm's efficient running time. Building on the previous trimming argument, we now bound the size of each trimmed list and derive a concise running time guarantee. After trimming, every pair of successive entries z and z in list Li must satisfy the multiplicative gap .z greater than 1 plus epsilon slash 2n. As a result, aside from the mandatory 0 and an optional 1, each list can contain at most log base 1 plus epsilon slash 2n of t additional values. We rewrite that logarithm in natural form. Log epsilon slash t plus 2 equals ln slash ln1 plus epsilon slash 2n plus 2. Next, applying the standard inequality ln1 plus x is greater than or equal to x over 1 plus x, and using epsilon slash 2n less than 1, we simplify step by step. 2n1 plus epsilon slash 2n ln t slash epsilon plus 2 is less than or equal to 4n ln t slash epsilon plus 2. Hence, each list contains on slash epsilon log t elements. This key result shows that trimming keeps our data structures small and directly controls the overall running time. Having established that trimming keeps our list small, let's introduce approx_subset_sum, a fully polynomial time approximation scheme for the subset sum problem. The algorithm takes as input a set S, a target T, and an error parameter epsilon. First, set n equals and initialize L equals 0. In the red boxed loop for I equals 1 to n, we tell 1. Merge L with a shifted copy that adds x to every entry. 2. Apply trim with parameter epsilon/2n to keep the list compact. 3. Discard any sums exceeding t. Once all elements are processed, we pick the largest remaining sum z and return it. This procedure runs in on squared poly 1/epsilon time and guarantees a 1 epsilon approximation to the optimal solution. Building on our previous discussion of the algorithm's performance, let's dive into the running time analysis. First, we show that each list L has at most 4nt/epsilon plus 2 entries. Next, we clarify how we measure input size. It's simply the total bit length needed to encode the target t, namely log t bits, plus the bits required for the set S. Combining these observations, we conclude that the overall running time grows polynomially in n and in 1/epsilon, so our algorithm really is efficient under these parameters. Building on that analysis, here's a concise summary of our results. Approx_subset_sum is a fully polynomial time approximation scheme for the subset sum problem. Its running time grows polynomially in the number of items, nan, and in the inverse of the error parameter, 1/epsilon. Even better, it always returns a solution within a factor of 1 plus epsilon of the optimal. Now let's dive into the proof that approx_subset_sum is a fully polynomial time approximation scheme for the subset sum problem. First, observe that the trimming step never introduces new sums. Every element in the trimmed list li also appears in its corresponding untrimmed list pi. Next, we define y trees in Pn as the optimal subset sum value, and z trees in Ln as the value returned by our approximation algorithm. The heart of the argument is to show that the ratio y no zz is at most 1 plus epsilon. Establishing this bound completes the proof that approx_subset_sum not only runs in polynomial time, but also guarantees a 1 plus epsilon approximation of the optimal solution. Before we dive into our approximation scheme, let's quickly recap the brute force algorithm for the exact subset sum problem. We start by representing our set S with size n and constructing a sequence of lists p through p. Initially, p contains only the sum 0. Then, for each element x in S, we form p by merging the previous list p with a version of that same list where x has been added to every sum. After merging, we simply discard any sums that exceed our target t. Once all n elements have been processed, the largest sum left in P is guaranteed to be the optimal solution. By carrying forward every possible partial sum at each step, this method explores every combination and never misses the best subset, even though it can be quite costly in time. Next, we'll see how trimming can dramatically speed up this process without sacrificing too much accuracy. Building on the brute force approach, here's the pseudocode for a fully polynomial time approximation scheme to subset sum. We begin by initializing L to contain just 0. Then, for each element x in our input set S, we form P by merging the previous list L with a version of that list shifted by x. This captures every sum that either excludes or includes x. To prevent exponential growth, step 5 applies the trim operation with parameter epsilon/2n. Trim prunes away any sum that's within a factor of 1 plus epsilon/2n of a smaller one, keeping only a single representative from each cluster of near duplicates. After trimming, we discard any sums exceeding our target t. Once all n elements have been processed, the algorithm simply returns the largest remaining sum z. By trimming at every iteration, we ensure each L stays small, guaranteeing polynomial running time, while still delivering a solution within 1 epsilon of optimal. Now that we've seen how trimming keeps each L small while preserving near-optimal sums, let's state the key lemma behind our approximation guarantee. We prove by induction on the index I that for every value y in P with y is less than or equal to t, there's a corresponding entry z in the trimmed list L satisfying. Y is greater than or equal to z is greater than or equal to y. 1 plus epsilon division slash 2n. Wild subi howlies left. In other words, each candidate sum in P can be closely represented by some value in L within a multiplicative factor of 1 plus epsilon division slash 2n. Since the true optimum y times lies in P, this lemma ensures there's an approximate solution z times in L for which y times is less than or equal to 1 plus epsilon division slash 2n to the power of n is less than or equal to 1 plus epsilon z times. That immediately gives us our final 1 plus epsilon approximation ratio. Now let's prove our lemma by induction on I. We want to show that for every element y in P with weight at most t, there's a proxy z in L satisfying. Desquo y div I 1 plus epsilon slash 2n is less than or equal to z is less than or equal to y. Base case, I equals 0. It's immediate since L contains exactly P. Each y is its own proxy. Inductive step. Assume the claim holds for I equals k. That means for every y in P, there's some z in L with. Y divided by dup by 1 plus epsilon slash 2n is less than or equal to z is less than or equal to y. Beal. Now consider I equals k plus 1. We form P by adding x to P, and then build L by merging two lists. Zan L shifted by x, each element plus x. Z original L. Because of this merge and the extra division by 1 plus epsilon slash 2n, at each step, every y in P still has a proxy z in L satisfying. Y vi 1 plus epsilon slash 2n is less than or equal to z is less than or equal to y. This completes the inductive argument. Building on our previous slide, we now give an inductive proof that, at each step I, every sum y in the prefix set P has a closely matching element z in the trimmed list L, satisfying. Y divided by 1 plus epsilon slash 2n is less than or equal to z is less than or equal to y. Let's start with the base case, I equals 0. Here, P and L both contain just the value 0, so the claim holds immediately. Now assume the statement is true for I equals k, every y in P has some z in L with the required bounds. We'll show it then holds for I equals k plus 1. Any new sum in P takes the form y plus x, where y element of P. By our induction hypothesis, y has a representative z in L. Adding the same element x gives z plus x, which lives in the shifted list L plus x. When we merge that with L to form L, the approximation guarantee is preserved. Y plus x divided by 1 plus epsilon slash 2n is less than or equal to z plus x, is less than or equal to y plus x, and that completes the inductive step. We've now shown the bound holds for every I, proving our claim. Building on our previous result, we now prove by induction on I that every element y in P up to t has a matching element z in L satisfying. No. Y divided by 1 plus epsilon slash 2n is less than or equal to z is less than or equal to y. Base case, I equals 0. P and L both contain only the initial 0, so the claim holds immediately. Inductive step. Assume at stage k that each y in P has a z in L meeting the bound. To move to k plus 1, we insert the next item x into both lists and then merge. L equals merge. L union x, L dot P equals merge. P union x, P. Because our merge procedure always ensures any two consecutive elements differ by at most a factor of 1 plus epsilon slash 2n. The new sum y plus x still finds a neighbor z in L satisfying. Y plus x divided by 1 plus epsilon slash 2n is less than or equal to z is less than or equal to y plus x, this closes the inductive step. After all n inserts, every element we keep remains within a global 1 plus epsilon approximation of the true subset sums. Building on our previous argument, we now prove by induction on I that every sum y in P, not exceeding t, has a matching value, z in L, satisfying. Y divided by 1 plus epsilon division slash 2n is less than or equal to z is less than or equal to y. Base case, I equals 0, is immediate. P and L both contain only 0, so the inequality holds. For the inductive step, assume the claim is true for I equals k. That is, for every y in P, there's a z in L with y divided by 1 plus epsilon division slash 2n is less than or equal to z is less than or equal to y. Now consider I equals k plus 1 and pick any element y dash in P. By construction, y equals y plus x for some y in P. From our hypothesis, we choose z in L, so that y divided by 1 plus epsilon division slash 2n is less than or equal to z is less than or equal to y. When we add x to z, we get z plus x in L. The trimming step may replace z by a nearby value, but it guarantees another element, z in L, with z divided by 1 plus epsilon division slash 2n is less than or equal to z is less than or equal to z. Chaining these bounds gives y divided by 1 plus epsilon division slash 2n is less than or equal to z is less than or equal to y, completing the induction. Hence, at every stage I, the list L retains an element within the desired multiplicative error of any sum in P. Building on our previous step, let's prove the claim for I equals k plus 1. Take any y in P. By construction, there's a corresponding element z twice in L that already satisfies. Y dash delike 1 plus epsilon slash 2n is less than or equal to z is less than or equal to y, die. When z undergoes trimming, the process guarantees another list entry z delay in L with cry. Z des slash 1 plus epsilon slash 2n is less than or equal to z is less than or equal to z. Chaining these two inequalities yields y derisk phi 1 plus epsilon slash 2n is less than or equal to z is less than or equal to y derisk. So every y derisk in P indeed has an approximating z in L. This completes the inductive step for I equals k plus 1 and shows that at each stage we maintain y divided by 1 plus epsilon slash 2n is less than or equal to z is less than or equal to y. Recall our induction hypothesis. At the ith step, every value y in P that does not exceed t has a counterpart z in L satisfying. Y divided by 1 plus epsilon slash 2n is less than or equal to z is less than or equal to y. Divide by, now let's focus on the final set P and its optimal element y times. By the same argument, there exists a z times in L with dot y times die equal 1 plus epsilon slash 2n to the power of n is less than or equal to z is less than or equal to y times. Notice that rearranging this inequality gives dot y times 4z times is less than or equal to 1 plus epsilon slash 2n to the power of n, which is precisely the bound stated in equation 35.26. Building on our previous bound, let's take a closer look at the sequence. 1 plus epsilon division slash 2n to the power of n. From equation 3.13, we know it converges to e caret epsilon slash 2 as n right pointing arrow infinity. By differentiating with respect to n, we see its derivative as positive, so the sequence rises steadily toward that limit. In particular, for every finite n we have 1 plus epsilon division slash 2n to the power of n is less than or equal to e caret epsilon slash 2. Finally, to wrap up our chain of inequalities, we invoke the familiar estimate dot e is less than or equal to 1 plus x squared whenever is less than or equal to 1, which completes the set of bounds we need for the proof. Building on our earlier monotonicity argument, we now show that as n grows, the expression 1 plus epsilon slash 2n to the power of n converges to e caret epsilon slash 2. First, differentiate with respect to n and observe that the derivative remains positive. This tells us the sequence is strictly increasing. Since it can't exceed its known limit, it must settle at e caret epsilon slash 2. Finally, we invoke the Taylor estimate for the exponential function. Whenever is less than or equal to 1, e canalem is less than or equal to 1 plus x squared. Substituting x equals epsilon slash 2 gives dot e caret epsilon slash 2 is less than or equal to 1 plus epsilon slash 2 plus epsilon slash 2 squared. And for 0 less than epsilon is less than or equal to 1. This is bounded by 1 plus epsilon. Putting these steps together yields the desired inequality. 1 plus epsilon slash 2n to the power of n is less than or equal to 1 plus epsilon and completes our proof. With that key bound in hand, let's recap. Approx underscore subset underscore sum is a fully polynomial time approximation scheme for the subset sum problem. We've proved that the solution it returns, y times, satisfies dot y times z times is less than or equal to 1 plus epsilon. So it always stays within a factor of 1 plus epsilon of the true optimum. And we've shown its running time is polynomial in both 1 slash epsilon and the input size n, meaning this algorithm is not only accurate, but also efficiently scalable. Building on that, we say an NP-hard problem is closed once it admits a fully polynomial time approximation scheme, or FPTAS. A classic example of a closed problem is subset sum. In practical terms, having an FPTAS means we can crank out solutions arbitrarily close to the true optimum within any factor 1 plus epsilon we choose. And we do it in time that grows only polynomially with the input size and 1 slash epsilon. It's a powerful way to tackle problems that would otherwise seem intractable.